Alright, so this is going to be the video for Lab 6, and so in this lab we're going to be making a complementer using the hex display. So okay, so the output is going to look like this. We have our two 7-segment displays. There's number 1 here, 2 here, number 3 here, number 4 here, and it just goes on like this. So yeah, you have 8 digits. So, and then we have our switches. So yeah, on our board we've got 16 switches and 8 7-segment displays. So for this lab, what you're going to do is we're going to use the first 4 switches such that these two are going to display the value of it. And then these two are going to display the complement of it. Hold on, let me see something. And it's going to read in an 8-bit value. So, okay, that makes more sense. So it's going to be these 8 switches that you take in as an input. So if they're all ones, like this one's a 1, they're all ones, then what do you think is going to go here? What's this number going to be? What's this number going to be? Well, it should be FF, because remember, the way you convert, oh, here, let me just pull it up. Oh yeah, this beautiful thing right here. I'd really recommend you guys just print this paper out. It's going to be very helpful. This out right here, this table. Let me get a screenshot of that. Okay. So we have 8 digits. If the first 4 are all physically up, like if the first 4 switches are all on, like if they're like if they're up, so that correlates to a 1 when they're all physically up like that. Well, according to this table, when you have four ones, that's F. So these four would make this one B. So those four would make the first one be F. And then the second four would make the second one be F. And if we were to do something like this, change this one up. Well, according to the table, that's 9. And you should know that that's 9 in binary. But yeah. So, yeah, these first two values in the 7-segment display are going to correlate to the inputs. But then you might be asking yourself, well, what happens over here? And the answer is that that's going to be the exact opposite of this. So, you see how when we have this switch input combination, it corresponds to this? Connect. Okay. It's not updating. Let me try and fix this real quick. Okay. It's fixed now. Okay. So we have this as our 8 inputs for our binary switch value on the 7-segment display. We should see 9F. And then on this side, it's going to be the complement of this. So the complement is going to be all the bits reversed. So it's going to be 0, 1, 1, 0, 0, 0, 0, 0. These four, that's 0. These four, that's 6 in binary. So you're going to see 6, 0. And according to the table, yeah, so 6 is that one, and 0 is that one. So yeah. So this is what all of this right here, this is what you're going to be demoing to me in your lab. And that's exactly what Morton asked you to build here. You see, that's what this is. the code I'm going to show you guys today, it's just going to be to really give you guys a really good idea of how to get multiple numbers to show. Because if you guys remember, even though so you got we have our 8 7-segment displays. Let's say we want to turn on the number 1. Well, you need to turn this one on and then this one on. But if you turn this cathode on and this cathode on, it turns it on for all of them. So you would see all of them be 1. Yeah, you know what I mean. So what you have to do is control the enable. So what you would do to have it be where only this one shows is you only enable the first one and then you disable the next. So if you disable them, it doesn't matter that there's a voltage that's supposed to turn this one on and that's supposed to turn this one on and this one on and this one on. It won't matter because it's not enabled. If it's not enabled, it doesn't matter what the cathode is. There's going to be nothing showing on that 7-segment display. And thankfully, there's an enable for each individual 7-segment display. It would be stupid if that was tied to, because then there'd be nothing you can do. Okay. So you might be asking yourself, well, and I'm pretty sure we did this in the last video, but it's good to just go over it again. Like, let's say we want to display the number 57 right here. Let's just delete all these. Or now we'll leave them. So we'll display the number 57. What we would need to do is we would need to enable this one first, which is I'm representing with that dot. We need to check. We need to set the enable low, I believe. Yeah. Yeah, if you set the enable low, so to 0, that's on, and then you would set the rest of them to 1, and that's going to be labeled your anodes. So if you do that, because the anodes for this one, this one, this one, this one, this one, this one, this one are all 1, they're disabled. Because it's active low, meaning the anode has to be 0 for it to work. So then what we would do is we would send the corresponding signals to make 7. And then we would do that. And then you might think, okay, well, we got the 7 down, so how do we make the 5? And the answer is you essentially do the same thing again, but instead you enable this one. And then you would change the cathodes to correspond to 5. So yeah. So if you do this, and then alternate between the two really, really fast, it'll conjure up the illusion that it's just a constant 5/7 because our eyes won't be able to detect it. Oh, and that's another thing. We're gonna have to use the clock divider module to create a very specific clock that can alternate between this and this fast enough such that it seems to our eyes that it's a constant 5/7, but slow enough that it has time to work. Because if we use the 100 megahertz clock, it's going to switch between this and this so fast that it's not going to have time to even turn on. And if we were to switch it too slowly, you would see 5 on with this off, and then 7 on with this off. So there's very specific clocks. Well, there's a very specific clock that we're going to use that has the right frequency or speed to do what we want to do. So this right here is what I would consider a very easy to understand program. This is about as simple as it can get, and this program really gives you a lot that you can do. So let's go through it. So to display a different number, remember, we have to iterate and change the cathode and the anode. Oh yeah, remember, cathode, that array controls this, anode controls the other one. Oh yeah, so that's what this is. Let's go through this first. So, okay, hold on. Oh, it's stuck to it. Let's crop that then. I do not want this right here to be stuck to this image. Oh, what? They're still stuck? Oh, wait, they're kind of not now. Weird. Okay, now that these are untethered, we can begin. So this module, let me move this out of here for now. So module did just set sexy show. We know what this does, but well, I'll do it up here. So this is our module. It has two inputs. Digit and DP. And then output of 7 bits. Well, you know, I'll just draw it. 1, 2, 3, 4, 5, 6, 7. Oh, let me draw it better. And then there's 3 of them here. I mean, 4 of them there. With our DP there. So, digit. What is digit? So digit is going to be a 4-bit value that we want to represent. So if digit is 1, 0, 0, 0, and let's say this is the order of significance, well then what digit set segs is going to do, oh then let's say this is tied here. Hold on. Yeah. Okay. So digit is 1000. What that means is it's 8, because that's what that is in binary. 1000, that's 8. So if you get that in, it's going to take those 4 bits and create a 7-bit pattern such that it turns this one on. So this would be high. It's going to turn this one on. This would be high. It's going to turn this one on. So where that goes back to there, there. So that's one. This one, and this one, and this one. So all of them, it's going to be like this, yeah. So all of them except that middle one. If this were to be this right here, that's A, because that's 10 in binary. It's 10. Decimal, binary, hex. If we send the binary value in for A, what digit set segs is going to do? It's going to send the following output signals to then make that A. So then it'd be like this. So all of them would be on except that bottom one. And DP, we're never gonna, oh yeah. Oh yeah, because 1, 2, 3, 4, 5, 6, 7, 8. It's because another output. Oh, we have our decimal point. Oh, and they're active low. So that means if it's 0, it's on. So then that means it would actually be in our decimal. Do we want our decimal on or off? We want it off, so it's going to be 1. Oh, wait a minute. Okay, here it says DP equals 1 means turn off decimal point. Don't be confused by that because down here they negate it. Because in reality, for this board, in order to turn it on, it needs to be 0, and to turn it off, it needs to be 1. So yeah, if we want to set A with no decimal point on, oh, what am I doing? So this is going to be 1. Let me see this real quick. That means a 0 is being passed in. And there's like an inverter circuit that changes it to be a 1. And these 8 outputs, that corresponds to the array of cathodes. And these 5 inputs are these. So if this input right here is a 1, it's going to invert it to make the output be a 0 to turn it on. But in our case, if we put in a 0, it'll invert it to be a 1, which will then make it be off. So that's how that works. So this entire table pretty much just does this, but for all different numbers. Okay, so now that you know how that works, we can get to the main code. So what we have, well, okay, then we instantiate this module down here. This is right here. So whatever the register of dig in is, and we set our decimal to 0, which means it's going to be turned off all the time. Because if decimal point 1 is on, decimal 1, pp1 is on, we passed in 0, so it's going to be off. And the reason why it's going to be off is because when 0 goes into the module, it gets inverted to become 1, which will then be active, which will then be high, which will then make it be off because it's active low. And then our output is CA. So what we want to do is we want to rapidly change AN and dig in. Because this is instantiated, what that means is that at all times, dig in, wherever it is going to go in there and update CA, the output, instantaneously. So if digin is 0000, it's going to control CA to output the 7 segment 0. If digin is 0001, it's going to instantly change it, the output, to be 1. If digin is 0010, it's going to change it to be 2, and so forth. So if you want to display a bunch of different values, you're going to want to change dig in very, very quickly. And one way to do that is to use a counter. So say we've got a counter. Oh, that's what we have here. If counts is equal to count plus 1 at, oh yeah. So remember we have a clock multi there. Which is made by this. So we have our fast clock here. And I'll just explain this first and then explain this. So we have our fast clock, CLC, and then we have a clock counter. On every positive edge, clock counter gets incremented 1. And this entire time, clock multi is just whatever, it's just constant. But enough times later, once this gets big enough and and clock counter gets big enough as to equal to with 2, it will alter it. And that's what this is. Because on every positive edge, it adds 1 to this register clock counter. But eventually, when you have enough of these cycles, clock counter is going to be equal to width 2. Oh, so yeah, that's the clock divider. And by setting width 2 to be equal to 10,000, that makes it be that perfect speed that makes it fast enough to switch very quickly. Oh yeah. So then we go here to pulsage, CLC multi. So this clock that got made from this clock divider, then on the rising edge of that clock, we increment a new count. So count will be 0 there at the start. And then count is equal to 1 there. Count is equal to 2 there. Count is equal to 3 there. And it just goes on and on until we get to 7. And then after that, there's a statement forcing it to reset all the way back to 0. So then the next positive edge, it'll it'll be 0. So yeah. So then what we do is we make there be a case statement. Where case of count, whenever count is 0, we set our anodes to have the first one be on and digin to be 5. So what's going to happen is it's going to pass. So here on this first rising edge, it's going to enable the far rightmost 1. So it's going to be like this, like look. So we got our 8 7-second displays. We got our 8 7-second displays. So only this one's going to be enabled. These will all be off no matter what. Because of this, remember, these 7 are 1, meaning it's off because it's active low, meaning it has to be 0 to be on. Indigenous 5, meaning zero, one, zero, one is going to be passed in, and then that's going to generate the needed outputs to make 5. So the 5 will be made there. And then on the second stage, uh, on the second stage, the second one's going to be enabled. All the other ones will not. And digit is 10, so then it's going to be A. And it's going to go down and do this. And then I added a special case where digit is equal to 3 plus switch. So with that one, as you can see, these four are going to be disabled, and that one's going to be enabled. So it's going to be 3 plus switch. So if switch is 0, it's going to be 3. If switch is 1, 1, 1, 1, actually, if switch is 0, 1, 1, 1, that's 7 plus 3. That would be 10. So it switches this. Hold on. So 10 in hexadecimal is A. So I'm going to do that. And if it was a switch to 0, 0, 0, 0, then it would be 3 right here instead of A. And what this is just an example of how you would update two values at once. So this value, dig R, that stands for dig result. And here, dig result is going to be equal to A4 plus the 4-bit switch input. So if switch is 0, 0, 0, like if the 4 switches are 0, then in these two, you're going to see A4. And if switch is 1, it'll be A5, switch is 2, be A6, and yeah. And if you add them all up, it'll go up to B3, because that's what A4 plus 15 is. Okay. So let me show you. So this right here is it. You got A4. And if I turn on a switch, both this one and that one go up by 1, which makes sense because of this right here. The fourth one, 1, 2, 3, 4, is going to be equal to digin, which is equal to 3 plus SW. So right here, when it's SW, the first 4 input switches is 0, it's 3. But then when it's 1, it's 4. When it's 2, it's 5, 6, and yeah, it just adds it up. And yeah, when you go to be such that it's past 15, it overflows and goes all the way around to 2. But yeah. And then for these two down here, remember, dig R is an 8-bit value that is equal to A4 plus SW. It's 8 bits, and remember, dig N is 4 bits. So you put the least significant bits of dig R in this one, which correlates to this right here, and then the most significant ones into this right there, because you want the most significant ones more to the right, which is why it goes in 6, not 5. So yeah, if jar is equal to A4 plus SW, but SW is 0, it's just going to be A4, but when we increment it, it goes up. So you can see when we make it equal to 3, A4 plus 3 is 7. If we were to add, say, 6, so it's going to be AA. Let's add a big number. Let's go to 8. Let's add 8. 1, 2. Let's see. Let's add another thing. So yeah, then when you add enough numbers, that digit there updates. Yeah. Oh. So yeah, that's how this works. And all of this code, I feel, is a lot simpler than other ways of doing it, because it's literally just yeah, I feel that this code is a lot simpler than Warden did, because it's just simply you're just incrementing a register called count 8 times from 0 all the way up to 7, and then you have case statement, or you can use an if statement where whenever count is 0, enable whichever one you want on, and then set dig in to be whatever you want. Actually, you wouldn't even need to use dig in. Like, if for some reason you find this confusing down here, you can just do this. You can probably just directly set your cathodes. So digit is 5. You just go to the one that's 5. Copy and paste that. Well, then you have to change it to be output reg, but I don't know, that probably would work if you just fully elaborated it on that way. But yeah, I feel like that's everything for this. But yeah, instead of displaying a bunch of random numbers that change with the switches, what you're gonna need to do, yeah, so instead of doing what I did here with this, you're gonna need to do this. Where instead of having all of them be filled out, where this one and then these two get changed by the switches, you're gonna have it be where this one, this one, this one, and this one are never on, but this one, this one, this one, and this one are on. And the value in these two is going to be directly equal to the 8-bit representation right here. And then the value here is going to be directly equal to the inverse of this 8-bit representation. So this is 1001, that would be 0110, and then 0 is there because it's opposite. So yeah, that's going to be your job. So that's kind of why I wanted to do this, just to show you guys how to make two things be updated at the same time, because that's something you guys are going to have to do. Yeah. If you want, like if you don't want to use this module, oh, like if you don't want to use this right here, uh, like if you don't want to use this, and it updated it. Then instead of just instantiating this, you can get rid of that and then have a statement be like, we get rid of that, and then do CA equals whatever you need to turn on the number you want. But I don't feel like that's as good of an approach because for stuff like this right here, that can be real weird. It'd be harder to do simple stuff like this. So yeah, this is a better approach. All right, well, That's everything I have for lab 6. Thank you.